Hello everyone, welcome back to video lectures on DSP sampling. Uh, so this is we had already discussed about basics of periodic sampling. The second lecture we discussed about frequency domain relationships of sample signals. Next lecture we have discussed about given a discrete time signal, how could you reconstruct back the continuous time signal. And in the previous lecture we have discussed about how could you process a continuous time signal in the discrete time domain, right? And in this lecture we would be discussing about decreasing the sampling of a discrete time signal. So essentially this lecture and the next two lectures would be more about upsampling and downsampling of a given discrete time signal. Okay, so with that, let me move to the notebook mode. So share the desktop with you. Just keep the setting proper. Okay, now let me hope you could see here, right? So what we do is, suppose now the problem is like this. You have x of n. Okay, assume that this has been obtained by sampling the continuous time signal with a rate nt. Then you want another signal x1 of n which is having a different value of sampling, let's say nt1. Okay, then where your t1 is not equal to t, this is the scenario. Then what we would like to see here is how are this x1 of n and x of n are related, okay, in both time domain and frequency domain, in both the time domain and frequency domain. This is of our interest to us. Okay, how are they related? One way to, so by the way, you might be wondering why you in the first place you want to either downsample or upsample a discrete time signal, the existing discrete time signal. There could be different reasons for it. One possible reason is once you are doing a discrete time processing, certain modules will process it at a particular bit rate. Okay, so for that purpose, when you give your signal, discrete time signal, to that particular, let's say you had you have taken the audio samples of this speech which I am talking at 44.1 kilohertz, for example, and assume that there is some block in your whole DSP processor, DSP kit, which processes things only at 20 kilohertz. Okay, this is there. In fact, for certain blocks they would do the processing only at a particular rate. So then what would you do? You would, of course, then you need to downsample it. Similarly, assume that I have recorded everything here, okay, and then I want to share with you the audio file. Assume I have recorded it 80 kilohertz, size is too big, I don't need that size. So that's also another scenario where I would like to downsample the signal that has been recorded. Okay, and then how can you do that? Either upsampling or downsampling is one of the key questions. So one way of either one possible way to either upsample or downsample is, for example, you have here, let's say, x of n, right, and you use some reconstruction filter, okay, similar to our third lecture, what we discussed in the third lecture, and from that you could get xc of t. Okay, and then here you now take sample. In sampling, you do the sampling of it, okay, at the rate of t1, and that should give you the x1 of n. So this is our first and second lectures there. Well, this you could do it, but this way of approach is not practical. So it is not a practical approach for particularly for three regions. It's not a practical approach. Why do you think we won't do it that way, but rather we would directly upsample or downsample in the discrete domain itself rather than moving to the continuous time domain? Is because of non-linear 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 analog reconstruction filter. This is one reason. Okay, analog reconstruction filter. Do you remember the HR of t? So that's infinite number of things are there, k from minus infinity to plus infinity. They assume that the signal has been recorded for let's say duration of 10 minutes. So then see how many values you have, and then the reconstruction will have some issue. You will somewhere you would cut it out number of values that you would take. Not only that, in practice, that's again in theory, in practice you will not get an ideal reconstruction filter as such, so there will be some losses there. Similarly, due to the digital to analog, the converter practical implementation will also have some issues. Okay, because of which there will be problems like quantization and other things. Okay, so this is not won't be ideal as we have shown. Similarly, if you had done it the way just we discussed it right now, it also requires conversion from, so sampling at t1 while you are doing it, it also requires from analog to digital converter. Okay, that practical implementation also has some issues, so that's not the way you do it. Okay, so would rather get it from right away from x of n itself. Okay, so what we would do is now is sampling reduction by n into, so in our current scope, what we would do is, that's why we would do downsampling right away on discrete time signal. Okay, or downsampling rate reduction. So more specifically in this lecture we would look at downsampling by an integer factor is what we are going to study in this. So sampling rate, what we would be studying in this lecture is sampling rate reduction by an integer factor. That's what we would study in this video lecture, by an integer factor. So what do I mean by that? Assume that I have a signal x of n. I want to downsample it by a value of m. Okay, and then the downsampled or decimated also is one word used for it. That xd of n, when I say downsample by m, what does that mean is x of n times m. That means if I am downsampling by 3, what does that mean? I retain just 1 in every 3 consecutive samples in x of n. Okay, so for example, if you want me to write in terms of the sampling period, so on the left hand side of this block, okay, sampling period is t here. If it is t here, then here what will be the sampling period here? X of nm. So out of m you are just keeping one sample, so that is turning, earlier it is t, now again out of that m times is there, so the sampling period would be mt. Okay, then what is the kind of questions that we would be trying to we will be able to answer at the end of this lecture is, for example, what is xd of e power j omega, what is its value? Okay, then what is the relationship between xd of e power j omega, how is it related to x of e power j omega? Okay, anyway in the time domain we had already written the expression there. Okay, that's fine. Then what about aliasing? So when do you get, is there a possibility of aliasing when we are downsampling it? If so, when could that aliasing could occur? These are some of the questions that we should be able to answer at the end of this video lecture. Okay, by the way, if I am getting x of n, and if I am looking at in terms of the continuous time signal, can you tell me what was the sampling rate at which we would be putting it? It's of course will be 2 pi by t. Okay, Similarly, let me call it as omega subscript s here. Okay, here sampling period is mt, so that should be 2 pi by mt would have been the where the copies would be kept if you are doing right away from the other one. Okay, so now let me, yeah, this discussion, what we will do now is these are the relationships that we want to explore. To do that, first let's do it, uh, let's get an intuitive understanding in the first place. Followed by that, we will do a through the diagram of these frequency spectrums. Okay, magnitude of the frequency spectrums, let's do the analysis, and after that we will do a rigorous mathematical analysis of the same thing. Okay, these are the degrees of complexities we would venture into. Well, so first of all, before doing any math or drawing anything, what is it that you expect here? If I have a signal x of n that has a frequency spectrum of x of e power j omega, now I am going to, the case I am considering is I am downsampling it. So what could happen? So if I give you the magnitude of the frequency spectrum of x of e power j omega, can you tell me the magnitude of the frequency spectrum of the x subscript d of capital X subscript d of e power? So I give you this. Okay, can you tell me this? That's the question. So let's see, how could we, for example, mathematically think of it is, suppose you consider that I am going to downsample by a factor 2 here. Okay, then what is it equivalent to? For example, x of n, I take it, you multiply it with an impulse train, okay, that has an impulse at every alternative n value, right? If I want to do it by m equal to 2, downsample it by a factor 2, it should have at every alternative. So the time period in the discrete domain is 2, in other words. Okay, so you multiply this, and then the whole thing you scale it by, so n by 2 times n you keep it. So still now your downsampled one is a value, is retaining values at 0, 2, 4, okay, 6 and so on. Now if you scale it such that you get them at 0, 1, 2, 3, you should be getting the other one, isn't it? So what could you expect here? So multiplication is there, then the scaling is there. The moment you are multiplying with an impulse train, discrete, this is not the continuous time impulse train but a discrete time impulse train. Okay, you are multiplying it a discrete time impulse train. What should it happen? There is a consequence of it is, in the frequency domain, is you are convolving this with the frequency spectrum. Okay, you are convolving in the frequency domain with the impulse things. Okay, so then what could happen? Multiple copies of this could get placed, that's one thing. Okay, and then there will be, of course, a scaling factor also comes, just like we had with the continuous time impulse train, right? That's one thing. And then there is a scaling happening here, because the values would be there at 0, 2, 4 and so on. So another scaling in the omega axis is what you could expect. So that's what you could perhaps expect intuitively when you move from x of n to xd of n. So now let's do a little bit more thorough job of this. Okay, we have not seen how much scaling, how much amplitude and how many copies. Let's do a bit more rigorous job here. To do that, let's start from the continuous time domain. How is, assume that I have, this is my xc of j omega, the continuous time signal on omega. Okay, this is my magnitude plot. Okay, and this being equal to omega n, this to minus omega n. Okay, now assume, so this is what. Now first let's see how we could obtain x of n. We mentioned with a sampling period of t we obtained that, right? So let's obtain here, we go step by step, at least for the first case. Is how does, for example, xs of j omega would look like? You still remember xs of j omega, hopefully. That's after multiplication with an impulse train, the frequency spectrum whichever you are getting, okay, before analog to digital conversion is excess of j omega, correct? What was the effect of that? You have the values, there is no scale, yeah, this is still omega here, this value if it is 1 here, okay. Now when you move to excess of j omega, right, here you get 1 by t, of course this would be omega n minus omega n, multiplication with impulse train, frequency domain, multiple copies are placed, right? So you had copies placed at omega s, 2 omega s, and so on, okay. Similarly here copies are placed at minus omega s, this is 0. For convenience, let me also assume here, okay, let me assume so that the plots would be clearer. So let's assume here that my omega s is equal to 4 times omega n. My t value is considered such a way that omega s equal to 4 times omega n. That means this whole thing is 2 omega n here, okay. That's how I do it. So similarly thing here, okay. So double the gap is there. This is excess of j omega. Now let me move to x of e power j omega, okay, magnitude of x of e power j omega. What would happen here? There is only scaling that would happen in the x-axis. So what was the relation there? Omega times t is equal to omega. So this is in fact 2 pi by t, right? I will get this magnitude will be anyway 1 by t here along the y-axis, there is no problem. What would be this value? This is equal to omega n times t, okay, omega n times t. Well, if I write it further here with this assumption, 2 pi by t equal to 4 times omega n, right, that implies omega n times t is equal to pi by 2, okay. So this is equal to pi by 2, obviously this is equal to minus pi by 2. And where will this another copy would be? At, yeah, with the same logic, okay, this anyway 2 pi by t into t, okay, pi by 2, there is a gap of pi, right, and then 2 pi, okay, I would have something like this. So this would be 3 pi by 2 because this is pi by 2, right? This is 3 pi by 2. I have pi here. Similarly, this is pi. So let me draw this, just this copy. Okay, this is what I would be getting here. This is my x of e power j omega. This is 2 pi. Okay, so I got x of e power j omega. Now assume that I am downsampling it further by m equal to 2. Let me take, assume, again here let me assume further, I want to downsample it by a factor of 2. Okay, let me draw that out here. Okay, I'll try to draw it from x of e power j omega a little later, but before that let me try to draw this right away from here, from xc of j omega. Let me try it out. Okay, it's m equal to 2. Okay, now if I look at now what is, let the corresponding sampling rate is what omega s dash is 2 pi by, okay, yeah, what is it that I want to draw here? Magnitude of xd of e power j omega. Okay, now the way I do it, is what is its equivalent sampling when I look from the continuous time domain, and from there I'm going to draw it here. So suppose this has been obtained when I do it by a sampling rate of t. Now my sampling rate is mt. So in other words 2t here. Okay. So omega s is equal to pi s. So that's equal to pi by t. What I have here is pi by t. You already know here that pi by t is what I would be getting. So you have copies now. Instead of 2 pi by t, I have copies at, okay, this is for example 2 pi by t, so somewhere here pi by t. Okay, I am going to keep a copy at pi by t itself now, right? And what else? So what about this omega n would, omega n would remain same. So this would be the case now. So this is equal to slightly write a little here. So this is pi by, a copy is placed at pi by t here, omega subscript. Okay, earlier it is kept at 2 pi by t, and of course this is omega n only. This is minus omega n. What about this magnitude? Well, when it is t, the sampling, it is 1 by t. Now it is 1 by your, this is equivalent to having a sampling rate of mt. So this magnitude will be equal to 1 by mt, correct? And of course then this is equal to minus pi by t, and so on. Okay. This, well, I have, in fact, this is not xd of e power j omega as such. Okay, this I have, whatever I have drawn so far is for, in fact, is for omega, when I have here omega. Okay, now let me have, instead of that omega, if I do it out, okay, you don't worry about the scaling and x-axis, but where this will fall down, let's see. So this needs to be multiplied by m, right? This needs to be multiplied with the time period. So what was the relation? Omega, so is it omega times t equal to omega. Okay, let me call t prime here. I need to get into, so the t prime here is mt, correct? So where do I get this? So this, in fact, this will be equivalent to, this would be equivalent to pi here. Okay, this would be equal to 2 pi. This of course will be 0. This would be pi. This would be 2 pi. Hope that is clear. How do I get it? Because this needs to be, for example, multiplied with mt. M is equal to 2, so that's multiplied with 2t. So I would get here, with that 2 pi I would be getting. The same logic here, this was actually omega n times t is pi by 2. Okay, multiplied with 2, you get here pi. Okay, so if you don't mind, I would right away take here the, I'll erase this. Hope now this is clear how we arrived this omega also. So what I would do is, I would right away write omega values here. For your understanding, I did it in steps, but now given that that's clear, this is going to be 0, this is going to be pi, this is going to be 2 pi, 3 pi, and so on, minus pi, minus 2 pi, minus 3 pi, and so on. Clear? So this is xt of e power j omega. Now, okay, so here also, this is of course, let me just, we have omega n by t equal to pi by 2. Just for clarity, let me simply write here pi by 2. You already worked it out now. Okay, now this is good. This we did it in our conventional way that we know by directly getting it from xc of j omega. Now let's try to get the same thing from here so that we could establish the relationships between x of e power j omega and the other one. So how could I get from there omega? Okay, I want to get again the same thing I'm going to plot, but how do I get it from here 1 by t? So you could see here, if you want to arrive it, equivalent one would be for example, this pi by 2 should go, yeah, by the way I should the scaling is looks, when I see it omega pi by 2 and pi, there is something here. So if you let me just redraw that also for convenience in the same scale. Okay, so let me draw it the whole thing. Let me erase this out. The same thing I am drawing, but somewhat similar to the scale that I have above. Okay, so for example, this is pi. Okay, this is 2 pi, right? So it was varying from 0 to pi. I'm not changing anything. I'm simply following a scale similar to the above. Okay, then again it goes to pi here, then this goes to 2 pi, and then comes down. Okay, this is 3 pi. Similarly here 0. Okay, pi, yeah, this is 0 minus pi and minus 2 pi. Okay, now that's fine. So come back here, you want to get it here from there. So first thing what we could do is you draw the first copy here, whichever is there, 1 by t is there. Earlier it was this, again 1 by mt is there. Okay, so whatever the magnitude is there, when I plot it here, that magnitude 1 by t is getting scaled, and also here that pi by 2, okay, is moving to pi here. That's one thing. So suppose if I scale everything, along the x-axis by half, right? So that should, so this is your pi, that should go to, this should give me, assume that I am scaling everything by 2 there. So then where are the copies I would get here? So for example, this, the second copy would go to, when I scale that, would go to 4 pi. Okay, 0, this is 0. Okay, this is 2 pi, that should go to 4 pi, and at 4, the second copy there, whichever I see, will go to this. And similarly here it would go to 0. Okay, this is pi, 2 pi, somewhere there. Okay, don't worry about that I don't want to go to the other end there. Okay, and this of course is 1 by mt. So a simple scaling across x-axis, notice that would give you a copy far away, not at 2 pi. Okay, now in order to get that, now what we should do is to indeed have to place one more copy here, which is this copy shifted by 2 pi. One more set of copies you have to keep here. This is the tricky part to understand. Okay, that's why I'm drawing it in two ways. Hopefully that should make things clear. Okay, the earlier one anyway, yeah, this would be okay. One, the scaled copy I put it in one color, and the shifted copy in one and the other one, right? So this is your pi, 2 pi, 3 pi. So what's happening here? So you could see the moment we have seen it's equivalent to multiplying with an impulse train. So that's additional copy. Unless you keep it, you won't arrive it here, right? So two things happening here. In fact, three things if you want to say it. Scaling along the y-axis, right? Then scaling along the x-axis. The third thing is placing copy. When you are doing by multiplication by a factor of 2 or downsampling by a factor of 2, one more copy is placed. If you are doing, for example, downsampling by a factor of 3, 2 more copies would be placed. So this is what you could figure out. Okay, Even without knowing this, you still understanding the whole thing, you could still draw it by just understanding that this is periodic over a period of 2 pi, and then you could, once you figure out what's the basic, how does this fundamental one copy behaves, then you could keep on placing the copies at repeating that because of the periodicity. But this is more systematic one. Hope this is clear. Yeah, in the first go it might not be clear to you, so try understanding, going through it yourself, trying to analyze yourself on that, and then it should be clear, right? So this is as far as from the diagram analyzing it. To quickly summarize this, the way we have looked at is, you want to downsample a discrete time signal. We assumed it has a periodicity of t. You want to downsample it by further by a value m. So that's equivalent to downsampling the continuous time signal with a periodicity of m times t. From that we figured out what is the frequency spectrum would look like for the downsampled version. Then we compared with the version with the periodicity of t. From that we could figure out that this is in fact equivalent to amplitude scaling, then scaling along omega axis, and then placing the multiple shifted copies of the same thing. Okay, so if you want to write an expression for here, for example, this m equal to 2, I could have written this as m equal to 2. So compared to x of e power j omega, I'll be doing half, amplitude change is half. Okay, and I have kept one copy of it but scaled by a factor of 2, which is x of e power j omega by 2. Then what I did is I did a shifting, and then of course of a scaled version. So x of e power j times omega minus 2 pi, right, by 2. So this would be the expression which I got from the figure, right? Hope all the three things are clear to you. Half coming from 1 by mt here, from 1 by t to 1 by mt. X of e power j omega scaling along omega axis is there. Okay, that by factor of 2 when m equal to 2, that has come. Plus you are keeping one more copy which is a shifted and scaled versions, or scaled and shifted version in fact. So e power j times omega minus 2 pi by 2. This is a very important expression, right? So you could already sense here by this time, if you keep on downsampling it, there is you could end up with aliasing. So how do you avoid, what you need to do to avoid aliasing? Let's discuss this out. Okay, what should we do to avoid aliasing? Well, for that what we do, let's start here. Let's call it as omega x of e power j omega. Let's call this value as omega n. In this case, of course, that's pi by 2. Let's call this as omega n, which is nothing but omega n. If you want me to give an expression, is nothing but capital times omega n times t is what I am calling as omega n. Okay, if I call that as omega n, what would be this value? If I call that as omega n, this value, what is this value? This is equal to omega n times m. This is further coming by a value of m, right? Is it not? Hope that is clear, because this is getting multiplied by, right? This is, so if you just take a look at here, so that's nothing but getting multiplied by m there. And what should happen to that? Omega n times m, in the, when you have small omega there, it should be less than or equal to what value? Pi value. In other words, your omega n should be less than or equal to pi by m. Very important result. Okay, so as long as the largest frequency of your discrete time signal is less than or equal to, if you want to downsample it by factor m, that should be less than or equal to pi by m. Then that is to avoid aliasing. So well, if there is a frequency omega n is more than that, what is the way to do? Low pass filter. You let the signal go through a low pass filter that has cutoff frequencies of pi by m, so that you will eventually get a signal which is having a maximum frequency of pi by m. Okay, hope that is clear. So how could I write it? For example, you have a signal x of n, okay, which is having a frequency more than this for the m that you want to do. You pass it through a low pass filter, okay, whose gain should be equal to 1, and its cutoff frequency omega c should be equal to pi by m. You pass it through that low pass filter. Then let's call the signal that you are getting, again you reconstruct back in the time domain, equivalent one is x tilde of n. Then you pass it through your downsampler so that there is no aliasing. Okay, so the downsampled or decimated signal for x tilde of n, let's call it as x d tilde of n. Okay, and of course then this e power, let's call it as x d tilde of e power j omega. Hope this is clear. That's what we do. You make sure that your maximum omega n you have is at max pi by m, depending on at what rate you want to downsample the x of n. Okay, let me now give you an exercise which you should be able to do based on the above discussion. Is that, well, let me take the same values that I have taken here. For example, omega is equal to 4 times omega n and everything, but now instead of 2 downsampling it by 2, I want to do it by the same signal, but I want to downsample it by 3. Okay, what else? I will retain this relationship still, that is omega s is equal to 4 times omega n. Omega s equal to 4 times omega n. I would retain this signal. Okay, and then let's draw various things. So this is what I would give you. So I will give you more like a fill in the gaps. Okay, for example, let me redraw whatever is there earlier for x xc of j omega. Assume that this is my xc of j omega, this is omega n. Okay, this is minus omega n omega, right? Now how would be the x of e power j omega? Did we already do this? Yes, that would remain same. X of e power j omega, by the way this magnitude is 1. We did x of e power j omega here, correct? That for these values x of e power j omega is having from pi by 2 to minus pi by 2, and you keep placing copies at intervals of 2 pi. Okay, you have this value from pi by 2, 0, minus pi by, oops, suddenly it's stop writing. Okay, minus pi by 2, and then yeah, you repeat that here. Okay, so that's you have that. Okay, and after that what I want you is, yeah, this will stop writing now for the reasons I don't know. Okay, so I'll stop here. Maybe then I'll give you the exercise and the mathematical derivation for it in another part B video, because if this pen is stopping to write, I need to restart, so the video would again stop. So I will take a break here. Okay, and we'll do that in the other video. Okay, so let's stop here. See you in the part B of this lecture, which is unexpected, but let's do it in the part B of this lecture. Yeah, see you there. That's where we complete this topic. Thanks.